Sure.
Okay, we'll start. Okay. So since there has been a long gap, most of this lecture will be a recall of what happened last time. So okay, so first we'll recall a few facts about unitary representations. So the first one is the obvious one. If H is a Hilbert space, then this is a group, and then we define a representation the group representation is on a Hilbert space H. It's just a group homomorphism from yeah, I should mention unitary. Sorry. So unitary representation of a group G on a Hilbert space H is just a group homomorphism from G to U of H. Then let me.
So is there any reason for it being called unitary?
Oh, sorry. Yeah. Yeah. So this thing I didn't define properly. So this U of H is the group of all unitaries. Sorry.
Oh, okay, okay.
Sorry. Yeah. Wait. Okay. So again, we'll define a couple of things that let xi be a vector in H. Then and so yeah, and pi is a unitary representation of G on H. Then xi is called pi invariant so in every group element keeps xi invariant and let this is K be a linear subspace of H. So same thing that every group elements keeps the subspace invariant. Okay. Then I mentioned this proposition last time that let K be a closed subspace so hence K is itself a Hilbert space. So if we have a group representation pi and if K is pi invariant, then what we saw last time is that the restriction of, I mean, if we restrict any pi of G to K, then that will again be a unitary on K. And the restriction, like G going to that restriction, will be a group representation of G on K. So if we define pi K from G to U K, then I of so this we saw last time, and further what happens is the perpendicular, I mean K perp is also pi invariant, and hence pi K perp as defined before from G to the unitary group of K perp is a unitary representation of G on K perp. So if we have an invariant subspace, we can restrict that representation to both K and K perp. So this only happens if it is a unitary representation. Then, so this is about unitary representations. Another thing we did last time was measure preserving actions. So is this visible?
Yep.
Okay. So in this context, we had fixed some things that G will always be a countably infinite group. Infinite group, and omega E mu is a probability space. Then we define what is a measure preserving transformation. So first of all, is a bijection on omega. We'll call it MPT for short. If both phi and phi inverse are measurable, and phi, so sorry, mu of phi inverse E is just measure of E for any measurable E. So this is the definition of a measure preserving transformation. And what happens is if we have the collection of all measure preserving transformations, so then this forms a group. Okay, and then we define what is a measure preserving action of a group on a measure space. So mm, so this is just the group. I mean, the group acts on the measure space in a measure preserving way. So this is the I'll just mention we'll use the usual notation for group actions. So if G is in G and X is in omega, we'll use say Gx. I mean to refer to this alpha of G of X. So this is what we usually do for group actions, right? So this is so we'll be using this notation. So then, yeah. So then another thing we had done last is this. So if we have a measure preserving action G on omega, then what we can do is we can get a unitary representation of G on L2 mu. So So alpha G inverse, or we can put in inverse inside the bracket also. It doesn't matter. So this gives a unitary So how does this thing, so this is an L2 function. So how does it act on points of omega? So this will have pi g of f acting on some point x in the measure space. We'll just give f of g inverse x. So first we act on x by an element of the group and then apply f on it. Okay. So I'll erase the left hand side. So yeah. So this is a unitary representation of G on L2 mu, and what we know is like regardless of the action, the constant functions in L2 mu, those will be invariant vectors of pi. So that is clear from this formula. If f is some f of x is some constant c, then pi g of x is just f of g inverse x, but this is again the constant c. So I'll just state that one is an, so one means the constant function one is an invariant vector for pi. And consequently, what we have is, sorry, is this visible?
Yeah.
Okay. So scene 2-1 is the one-dimensional subspace of all the constant functions. Okay, so yeah, so then this thing, so see this remark. So this is saying that any invariant subspace will again have, I mean, restricting any representation on any invariant subspace will again get a unitary representation. But here that thing is not very interesting because this is just every group element takes any vector to itself. So, and that is independent of the action. So that is not what we are interested in. So what we'll mostly be focusing on is the perp of this space C into 1. So yeah, so I'll denote by into mu 0 equal to C into 1 per, and I, so I'll just say call this pi 0 from G to the unitary group of L2 mu 0. So again pi G of f of x is f of G inverse x. So this thing will be the same, pi 0 G, because this representation is just inherited from our original representation pi. Okay, so yeah, so this representation pi has a name. So in standard literature, it's called Koopman representation. And this pi naught we'll refer to as the deleted Koopman representation. So this is one part which I forgot to mention last time. So this is something new, this deleted Koopman representation. So this is because we are deleting a one-dimensional subspace from the whole space. Okay, so I am calling this L2 mu 0. So that is because we'll explicitly say what this subspace is. So recall that for f and g, if f and g are in L2 mu, then their inner product is defined as integral f g bar d mu. So the perp of this space is just all the functions whose inner product with 1 is 0. So hence f is in, this is if and only if inner product of f and 1 is 0. But this is if and only if integral f d mu. So this L2 mu 0 is the space of all L2 functions whose integral is 0, or as probabilists say, expected value is 0. Okay, so yeah, so these are like, I think, the prerequisites out of the way. So I'll again recall what we mean by ergodicity. So I hope I have some time left. What time is it?
9:30.
Okay, okay. So yeah, so again we have now measure preserving action alpha on a probability space. So we define Oh, sorry, this is a measure preserving action. So yeah, so we defined ergodic as we take uh, any measurable subset which has positive measure, then it's so non-zero measure, then its orbit will almost be the whole of omega and under the action of G. So alpha is called ergodic if for every measurable E, if so this is like saying it is a like a transitive action. Then second thing, so we'll define what is an alpha invariant set. So so that means by applying G on this measurable subset, it doesn't change E much for any for any action of any group element G. So this means the measure of the symmetric difference is 0. Okay. And third, so this is like it is invariant in the traditional sense that it keeps the whole set fixed as it is. The action keeps the whole set fixed. Okay, so now the last thing I did in the previous lecture was state a proposition given equivalent conditions for ergodicity. So I'll state that again. Alpha is acting on, this is a measure preserving action. Then first was greater. So if we have two sets with non-zero measure, then there exists a group element such that if we act that thing on A, then it intersects with B non-trivially. So that is the second condition. Third condition is this thing means that the action alpha doesn't leave anything invariant. So if it leaves something invariant, then that thing is almost nothing, or it is almost the whole thing. And the last condition is the same thing, but for strictly alpha invariant. Okay, so this is where we left off last time. So Yeah, most of these are left went away in recalling things. So yeah. I'll prove this now. Okay. So first, since the action is ergodic, we have because the measure of A is positive, then what happens is that so B we are breaking into two disjoint sets, B intersection this thing. So whatever is in B and this thing, and whatever is in B but not in this thing. But so I'll just say B intersection this thing complement. But this thing is a this second set is a subset of union G belongs to GA complement, and hence its measure is 0 because the measure of this set is 1. So so the measure of this second set is 0. So this is just but this set is like we can distribute over the union. So then what we have is measure of 0 less than measure of B. We already know this thing is positive, is less than or equal to summation. Since so this is where we are using the fact that G is countable. So hence there has to be some element G in G where this measure is strictly positive. So this proves 1 implies 2. Then 2 implies 3. So so suppose E belongs to A is alpha invariant. We need to show its measure is either 0 or 1. So suppose measure of E is not in 0 or 1. Then what we have is measure of E has to be positive. But since the measure is not 1, the measure of its complement is also positive. So we can apply 2. So hence there exists G in G. What's that? So this is like all, this is the set of all things which are in GE, but which are not in E. But then this thing is a subset of the symmetric difference of G with E. But this thing has positive measure, so this thing should also have positive measure. So this proves 2 implies 3 and 3 implies 4. So if something is strictly alpha invariant, then it has to be alpha invariant, and hence its measure will again be will be equal to 0 or 1. So this thing is trivial. So what we'll now do is 4 implies 1. So we have to show that the action is ergodic. So let E to show so we have to show the measure of the orbit is 1 of E. But this set is strictly alpha invariant because like if something is in this set, then it is in G1E for some G1 in the group. Now, if we apply any G to that thing, to any element in G1E, then that will be in G1E, which is again in this set. So this union is alpha invariant. So but since this is a group, the identity element is in the group, and that identity element applied acting on E will again give E. Hence, yeah. So hence, since this thing is alpha invariant, we have its measure has to be 0 or 1. But since identity element of the group acting on E will again give E, we have E is a subset of hence measure of this union is greater than or equal to measure of E, which is strictly greater than 0. So this thing can't be 0, so it has to be 1. So this again, this proves 4 implies 1. So we have proved this proposition giving various equivalent conditions of ergodicity. So what is the time? Hello.
सैम बोलो क्या टाइम हुआ है?
9:45.
Okay, so yeah, Sampurna wanted a break. So
Yeah.
Pause for. So can you pause the recording for 5 minutes? Okay. ये शुरू हुआ?
हाँ शुरू किया.
Okay, so our next aim will be to like give some more equivalent conditions for ergodicity. So for that we'll need some digression. So let's see. So we start with X, which is a topological space. So I'll recall that B of X, which is the Borel sigma algebra on X, is the smallest sigma algebra containing open subsets of X. So yeah, so this is the Borel sigma algebra. So we'll give some result. So X will start with second countable T1 topological space. T1. T1 is all singleton sets are closed. So and we have nu, which is a probability measure. Nu is a probability measure on X on the Borel sigma algebra. And suppose measure of any measurable set is either 0 or the whole thing, which is 1. So then, so one simple example of such a thing will be that the measure is concentrated at a single point. So the measure of the any measurable set is 1 if that point belongs to that set, and 0 if it doesn't belong. So what we claim is that in this context, when this thing is a second countable T1 space, such a measure will always be concentrated at a single point. So then there exists a point x0 in X such that the measure of the singleton x0 is 1. So we'll prove this. So since X is second countable, we have a countable basis. So let this be a countable basis for the topology. And we can always assume that the whole X lies in S. If it is not, we can just put take S union capital X, singleton capital X. So okay. So now we'll define a subcollection of S. So let U belongs to S such that so all open sets in all sets in S whose measure is 1. So first thing we observe is S1 is non-empty because X is in S1. So then since S1 is a non-empty family, we can take intersection of all the sets in S1. So okay. So now we claim that the set E0 has full measure, that is measure 1. So first we see that E0 complement is the union of all U complement where U varies over S1. Means this is equal to and since nu of U is 1 for any U in S1, this is just 0. So So we'll pick any point in E naught. So in fact, E naught will be singleton, but we won't need to prove it, and we won't prove it. So what we'll just prove is that the measure of singleton x naught is 1, which is what is required. So, yeah, sorry, we'll claim this. So suppose not. Then what happens is, since the measure of any set is either 0 or 1, we have the measure of singleton x naught is 0. So hence measure of x minus x naught is 1. But since the space is T1, this x minus x naught is open in X. But okay, so since S is a countable, I mean, since S is a basis, there exists a subcollection of S such that the union of all elements in this subcollection will be x minus x naught. So hence, there exists S2 subset of S. So is this below line visible? Bottom line?
Yeah.
Yeah.
Okay. 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 So hence, since S2 is countable, we have okay. Since one is less than or equal to this sum, hence for some u in S2, this thing should be non-zero. But hence nu of u naught will be 1, since every set has measured 0 or 1. So then u naught will belong to this S1, since that is how S1 is defined. But x naught is in E naught, which is the intersection of everything in S1. So hence E naught will be a subset of U naught. So x naught is in U naught. But what we have is, since but U naught is in S2, and hence U naught is a subset of x minus x. So this means x naught cannot belong to U naught. So this is a contradiction. So hence the nu of x naught will be 1. So this proves our lemma. So we'll call this lemma 1. So now, so now recall what we did in the previous lecture, that if we have omega 1, A1, mu1 is a measure space, and omega 2, A2 is measurable space. And if we have phi from omega 1 to omega 2 measurable, Then mu composed phi inverse from so this is in fact the first thing we did in the previous lecture when we were discussing the change of variable theorem. So you take a measurable subset of omega 2, pull it back into omega 1 and apply mu. So that gives a measure on omega 2 a2. So if we have any measurable function from a measure space to a measurable space, then we can push forward that measure on the second measurable space. Okay, so now we lemma, another lemma. So that this so this second lemma will directly follow from the first one. Okay, so omega mu is a probability space, and X is second countable P1 topological space, and we have a function f from omega to x measurable, where x we any topological space we will always consider with its Borel sigma algebra. Then suppose so suppose the measure of f inverse of E is either 0 or the whole thing for any measurable subset of x, then we have that f is constant almost everywhere. So you can see that this thing follows directly from the first lemma. So what we do is we take from this remark above, mu composed f inverse is a measure on x dx which satisfies lemma 1. Hence this measure is concentrated on at a single point, so hence there exists a point in x such that hence f is constant almost everywhere, because f inverse of x naught, so almost every point in omega goes to x naught. So yeah, so this proves the second lemma. So this is the main one that we'll use instead of lemma 1. Lemma 1 was just a convenient way of proving this. Okay, so now we'll give a few more equivalent conditions for ergodicity.
Kirna, the left corner is a bit invisible.
Oh, should I move it? Okay, I'll write it.
A little bit. No, it's okay. A little bit more. You should move it a little bit.
Move to the right.
Yeah.
Okay.
A little bit more. Yeah, that's fine.
Okay. Okay, and wait, we'll also fix a p between 1 and infinity. So we'll give an equivalent condition related to LP of mu. Okay, so then first is for all f. So if composed alpha G inverse is f almost everywhere, then f is constant almost everywhere. And third is that so here I don't need to mention almost everywhere because that is included in the definition of LP. Okay. So what's the time? Like, should I prove this or maybe we can do this next time? Like after this lemma, this is actually quite easy.
Okay.
So sorry?
I was just going to ask how much time it will take to prove it.
Maybe 10 minutes.
Yeah, 10 minutes, that will work for me. I don't know about others, but that will work for me.
Yeah, 10 minutes is fine for me.
Yeah.
Okay. So
Chilma, just one question. Can you remind me again what's the meaning of ergodic? Again, sorry. Alpha is ergodic. What does that mean?
okay, so in this proof, what we'll be using is that so we have a action of G, then if G is equal to E for all, so E is a measurable set, and if GE is equal to E for any group element G, then the measure of E should be either 0 or 1. So alpha doesn't keep anything invariant, unless that set is either the whole thing or almost nothing.
Okay, thanks.
So yeah, so that is the condition we'll be using in this proof. So yeah. So first we'll do 1 implies 2. So then, yeah. So to prove 2, we'll use this lemma. So we'll show that measure of F inverse C will be either 0 or 1 for any measurable subset of C. And since C is second countable T1, everything is fine. So to show this, we'll show that F inverse C is alpha invariant. Okay. So yeah. So we claim okay. So yeah. So to show this, we will show This is a subset of this set. And since f is equal to this thing alpha composed f composed alpha g inverse almost everywhere, this set will have measure 0, and so this set will also have measure 0. So this is easy to see. So if x belongs to G f inverse E, symmetric difference f inverse E, then case 1 we take x belongs to f inverse E. So x hence x is not in G of f inverse E. But then G x equal to G of G inverse x. So what this means is that G inverse x is not here. So G inverse x is not in f inverse E. So what this means is that if since x is in f inverse E, we know that f of x is in E, and f of G inverse x is not in E. Hence f of x is not f of G inverse x. So hence x is in this set. So similarly, if we assume x is not in f inverse E, that means since x is in the symmetric difference, we get x is in G of f inverse E. Hence, again, G inverse x is in f inverse E. So f of x is in E, but f of x is not in E, but f of G inverse x is in E. So f of x cannot be equal to f of G inverse x. Hence, again, x belongs to okay. So hence this hence G is a subset of this. And hence the measure of this thing is 0. But since alpha is ergodic, that means measure of f inverse E. So this is for, so we fixed one G and showed this, but the small g was arbitrary. So this is for all G in capital G. But alpha is ergodic, so measure of f inverse E has to be 0 or 1. Since alpha is ergodic. So hence by lemma 2, f is constant almost everywhere. Okay, so this proves 1 implies 2. So now we'll show 2 implies 3. But that is trivial because if we take any element in LP mu and take some representative, then that function will satisfy this. Hence, by 2 it will, since it is measurable, by 2 it will be constant almost everywhere. And hence it will be some equal to some constant in LP mu. So 2 implies 3 is trivial. Then 3 implies 1. So what we will claim is that if we have E is a measurable subset of omega, then if we take the characteristic function composed with alpha G inverse is characteristic function of G. So this is the claim for any E. So this means that so any point X is just characteristic 1E of G inverse X. This is equal to 1 if G inverse X is in E and 0 if G inverse X is not in E. So that is again 1 if X is in G and 0 if X is not in G. Hence, so this is equal to characteristic function GE of X. So this claim we have proved. So now let E belong to A be strictly alpha invariant. So we have to prove that alpha is ergodic. So we have to prove measure of E is either 0 or 1. But then whatever P is, we know, since this is a probability measure, we know that the characteristic function of E is always in LP mu, since the mu is a finite measure. So the 1E composed alpha G inverse is 1 of 1 GE, which is true for any measurable set. But now this E is strictly alpha invariant. So this is again 1E. So this characteristic function of E satisfies the hypothesis of the 3. Hence 1E is constant almost everywhere. But 1E takes value 1. 1E of X is 1 if X is in E, and it's 0 if X is not in E. So the only way for the function to be constant is that the measure of E has to be 0 or 1, in which case 1E will be equal to 1 almost everywhere or 0 almost everywhere. Okay. So this completes the proposition. So I'll stop here, and next time we'll using this condition, we'll relate this thing to the Koopman representation, and maybe we can also see some examples.